Good evening, everyone. I hope everyone's doing well. I want to come on and record a lecture for chapter 13. And so, what we'll do for the next 2 weeks, I'm going to record today's lecture um, this evening. And so, you'll have it for chapter 13. I'll also record a lecture on chapter 14, which is talking about generalizations. Chapter 13 talks about inferential statistics. What you could use this chapter for those who, again, download the PDF version of the textbook, is looking at the analysis that you're going to use for your proposals. This chapter talks a lot about the different types of analyses, statistical analyses that we use as researchers. And so it'll be really, really helpful for you to use this as a tool for this chapter to identify what those statistical analysis um, procedures that you may use for the data that you collect. I'm available to talk through it. But again, this chapter specifically talks a lot about that. And it'll be really helpful as you begin to talk about the results and the ending of that method section. You know, what do you plan to analyze? How do you plan to analyze the data that you get? Because when you talk about your expected results, those results have to kind of match the statistics that you use, right? So I have to be able to see what stats you use to get the results that you mentioned in your anticipated results, and then the conclusion. Okay. So what I'm gonna do, go ahead and share my screen. Go ahead and get to the lecture, and then once we get done, uh, again, I will make any announcement that I have at the end. Okay. All right. Okay. But again, welcome back. So again, understanding research results, we're looking at statistical inference. And so what we do here is when we're talking about statistical inference, we're talking about using samples. And we'll talk about this a little more specifically, using a sample that we get from a population. We use that sample to then draw conclusions about that population. And so we'll talk about the likelihood of you being able to get a large enough sample that encompasses an entire population is very unlikely. So what we do in statistics is we use the samples that we get out of our sampling frames, and then we make sure that we can make and draw those inferences to the population. Okay, here are the objectives here. And so what we're going to do, we're going to work through talking through a lot of the things that kind of a review for what we learned in statistics. So we'll talk about the alpha level. We'll talk about statistical significance, type 1, type 2 error. We'll talk about power and effect size. All of those things are really, really important as we move into some of the things that you'll be doing in experimental psychology. Knowing the terminology is really important for those who are going to graduate school and will likely do a master's thesis or a PhD dissertation. You're going to need to know this terminology, not so much word for word, but you do need to be familiar with the terms and the verbiage. Okay. Just to review, again, we talked about research results. We talked about descriptive statistics, and correlation. And we mentioned how to present data that we get, right? So we describe it using the mean, median, and mode. We use variance and standard deviation to give us an idea of what that data looks like as far as it being in a distribution. And then you can visualize it using various graphing techniques. We talk about pie charts, graphs, bar graphs, line graphs, frequency, polygons, and histograms. Okay, and so all of those things will be important. Again, as you do a real research project, you'll use descriptive statistics, and you'll also use inferential statistics to describe what's happening in your sample and your data. Okay, but again, when we talk about inferential statistics, it allows us to do two things. So the first thing is that it allows us to assess how confident we are that our results reflect what's happening in the true population, right? So if I have a research project, Kanisha is doing a research project on the effectiveness of a ACT uh, academic workshop, right? And she wants to see if she gets a group of students, maybe 15 to 20 students, she's going to test them on the ACT before they take part in this intervention ACT workshop. They take part in that, that first pre-test ACT. They take this 6-month period and they're going to work on all the different skills they need for the ACT. After the culmination of that program, they're going to take a post-test, and that will be another ACT. And she wants to see if those scores increase, right? And so if she has a large enough sample size, she can be pretty confident that that particular program is effective. And so if she gave it to any student, that their average score, maybe an increase in the ACT score, is going to be great. The second thing is you want to assess the likelihood that your findings will occur if you're able to repeat this study over and over and over again. So, if you want to do this intervention for one group of 20 students, you do it again, you see a similar trend, maybe you do it for several years and you continue to see a lot of progression in ACT scores based on the intervention. That means that I can draw an inference. I can be confident that intervention is working, and that's what we want to see. Okay. But again, with what we do as researchers, it's almost impossible to study an entire population, right? So I couldn't take an entire population of a school and send that entire population through a intervention like the one I mentioned before. So what I could do, and what many of you are doing, is you're taking a sample, either random sample or convenient sample. You're taking a sample out of a population, and then you're going to use the results that you get from that sample, and you're going to try to draw inferences or a conclusion back to the population, right? So it helps us answer those questions where I want to know, is there effect? Is there a difference? Is there a relationship? And I want to make sure that I have a more representative sample so that it can be generalized. And we'll talk about generalization in the next chapter, but I want to be able to generalize those results to the population and to everyone in the population. Okay. So, just hypothetically, we talked about the experiment where we had groups of students who were observing a model participating in some aggressive behavior. And what they saw was those who had a model who had an aggressive model versus those who didn't, the acts of aggression were higher in those students who had an aggressive model versus those who didn't. And again, they took a sample of students, right? But if that sample was large enough, they could then make inferences to the population. So any young person who has an aggressive model is oftentimes going to exhibit more aggressive behaviors than those who do not. And so we're able to draw those conclusions based on a sample and based on research that's done over and over and over again, like we said in replication. Okay. So again, here's an example. We talked about this data in chapter 12, right? So you have the number of aggression or acts of aggression, right? The average number. You got the mean here listed at 5.20 for the model group, and then for the no model group, you have a 3.10, right? So you see that there is a difference between the model group and the no model group, with the no model group having fewer acts of aggression than the model group. The standard deviation or the variance, so again, that's how spread out the scores are. Again, you see that they're very, very similar. There's not as much variability in the scores, which is good, right? You want to see scores that are pretty closely tied together between the two groups, okay? And then both of them have a sample size of 10, right? So we got 10 students or 10 young people in the model group, 10 in the no model group. And we'll talk about how we assess those differences. But with inference statistics, we're going to use those mean differences. We want to determine if this is a significant effect, right? Is observing an aggressive model effective? Is it showing me a significant difference between those who are in the model group and those who are not, right? Is it making a big difference, or is it just random? Is it just a random chance or a random happenstance? Okay. And one of the big things that we want to see happen when we see those 10 young people in the first group, in the model group, 10 in the no model group, you want to make sure that those two groups are similar, right? You want to make sure that they're equivalent. Because if they aren't equivalent, then there are going to be more factors, those extraneous variables that we talked about, those things that are outside of our control that influence the results. When we make those groups similar, equivalent, then we eliminate a lot of those extraneous variables. And then the dependent variable, the one that we're measuring, is again based on the treatment, whatever that treatment is. So that aggressive model is having an effect if, in fact, those two groups are very, very similar and equivalent in their characteristics, right? So again, when I make those two groups the same, then I know that the dependent variable must be due. Any difference in the dependent variable must be due to the effect of the independent variable, either being in the model group versus not being in the non-model group, right? There, obviously, with anything, since all of us have unique differences, um, when you're looking at two groups of individuals, there are always going to be differences, right? The difference between the model group and the no model group, there's always going to be some difference because of the individual differences among the groups, right? Even among the individuals in the particular groups, right? So I'm looking at the model group. That's why you see those individual differences. You see those differences in those scores. Not everybody's the same. People have different experiences, and so you're going to see those differences there. And again, that random, unsystematic error that they speak of is, again, those unique differences that we have as people. We're just all going to be very different in how we act and how we behave, right? So just because we're African Americans or white, again, we're all very unique and different in how we behave, our attitudes, and our behaviors. Okay. It says inferential statistics allows researchers to make inferences about the true differences in the population on the basis of sample data. So that's why we use samples. We have a total sample size of 20, 10 in the no model group, 10 in the model group, and we use those samples to then draw conclusions about the differences in the population, right? So if we see a significant difference between the aggressive behaviors in the model group versus those in the no model group, we can be confident that in the true population, that those differences are going to be very, very similar. Those who have an aggressive model that they look at and observe are going to have higher incidences of aggressive behavior. So we make that inference. Okay. Again, it also gives us a probability that our differences that we see reflect the real difference. That's what I want to see. I want to see the real difference. So it says that we give our own self a probability as a researcher, and if that probability is low enough and the difference that we see is rare enough, then I know that there is a significant difference and that the differences are real. They're real, actual differences. They're not just due to random, unsystematic error. That's what I want to see happen. Okay. The first thing, and again, as we learned in our statistics class, you have different steps, right? So when we talk about hypothesis testing, again, we're making an inference. We're also making a guess, right? So in order for us to understand what's happening in our research, we have to be able to hypothesize first, and we've done that in your proposals. You have a research hypothesis. You also have research questions, and the research hypothesis is telling me, you know, is there a difference? Is there not a difference? Are there effects being made? Is there a relationship happening? We're looking at those hypotheses, right? The first step, again, is stating those hypotheses. You have what we call a null hypothesis. And the null hypothesis is saying that the means that I have, there is no direct difference at all. There's no effect, no difference, no change, right? And it's all that's saying is when I look at those means, those population means, they are equal, and they're equal because of just the random error, right? The only difference that I see is just random error, right? Individual differences is just random unsystematic error. That's the only thing causing the differences, right? The research hypothesis, however, says that those two groups are in fact not equal, right? And that means that the independent variable having those two groups has an effect. So looking at the model and observing the model versus not has an effect on those young people, right? So the number of aggressive behaviors is impacted by that model, not just by random happenstance, okay? And when we see statistical significance, this is saying that there is a low probability that the differences that I see between those two samples, say the no model group and the model group, is due to random error. Right, so there's a small probability. That means it's very rare that those differences that I'm observing is due to just some happenstance, some random error. It's due to the effect of looking at the model, having a model, aggressive model versus not. Okay? The second step is we have to set our probability, right? We have to set that level of rareness that we want to see, right? And usually we'll talk about it when we talk about alpha level. Your alpha level or your significance level is that probability, right? That's that level of rareness that I want to see. I want to see the usual is at 5%. Usually that's some of the other conventions, 5%, you got 1%, and then you have 0.01%. Those are three conventions that are usually used to set that probability. But when we talk about probability, probability is that likelihood of the occurrence of some event or outcome. We all have and make probabilities all the time, right? When we look at the news forecast for the weather forecast, and they say we have a 75% chance of rain, right? That's a probability, the likelihood of that outcome, right? If it says 75%, that's a pretty good likelihood that it may rain. If it says 10%, then we may not grab the umbrella because again, it's only 10%. It's not that likely. Or when you are thinking about passing a class, right? When I used to register for classes, I registered, I would look at the particular class, I would look at the description of the class, and I would look at, maybe the difficulty, right? There's a good, maybe 75, 85% chance that I'm going to get an A in the class, right? So I go ahead and take it, right? Especially, with all the classes that I was taking and having to take in economics, I would choose the classes, especially during different semesters. So during football season, I would probably take a lighter class, easier class, so that I have a better opportunity or likelihood of getting an A, right? So we make probabilities all the time. In this class, if you came into the class and you were like, man, I got about a 95% chance of getting an A. That's a pretty good likelihood. But your behaviors have to, again, match that, right? If you're confident that you're going to get an A, again, the behavior, the attitude, all those things have to come into play, okay? But again, an example of what we use, I think in the textbook, if you had a friend who what we call had ESP, extrasensory perception. That means they have either psychic behaviors where they can predict the future, or they can logically, it's kind of illogical, but you can be thinking something and they can pinpoint it. Or think about this. So there are some individuals, I don't know what your room looks like, right? But you have a map of your room in your mind. A person with ESP can look at that and think and know they've never seen your room at all. Never been to your house, never been to your dorm room. But just the mere fact that you know the room setup, they know it because you know it, right? And they can tell you where everything is in that room, right? Some people have that gift, right? And how would I know that? Oftentimes we do research on that. Right. So say you have a friend, you have 5 cards, and each of those 5 cards has a symbol on it. And what you do is you're going to do 10 trials. So you're going to go through those 10 cards. You're going to go through those 5 cards twice. And you're going to give your friend an opportunity to prove if they have ESP or not. So what happens is what they do, on average, there's a 20% chance, right? 20% chance that you're going to get it right? That's that's probably average, right? You can guess two cards out of 10, right? You can guess 3 cards out of 10, and it's that's pretty cool, right? But if it gets to the point where you're guessing 5, 6, 7, 8 cards, right? The likelihood that you're going to be able to guess those, the probability is really, really low, right? So if I have someone, maybe my friend guessed 7 cards, 8 cards, man, the likelihood, the probability that he's going to be able to guess 8 cards correctly, that's not just random, right? You can randomly select and guess 2, right? But you can't randomly guess 8, right? There has to be something there. The likelihood that you're going to guess 8 is really, really low, right? The probability is really, really low. That alpha level is, again, that probability required for that significance, right? So if he guessed 2 or 3, that's not all that significant, right? Anybody can really guess those. But if he correctly guesses 8, 9, oh, I know that, yeah, that's significant, right? That means he either has ESP or he's a dang good guesser, right? So again, when we set those probabilities, when we set those alpha levels of the significance level, we're looking to see how rare something is. And if the differences that we find in our research exceed that rarity, then I make that claim that there's a significant difference, right? And so that's what we do. Um, the sample size makes a big difference too, right? So if I did this study with just my friend and it's just 10 trials, and yeah, he guessed 7 out of 10, right? But what if I gave him 100 trials and he's guessing 80% of the time correctly? That sample size increased to 100 instead of just 10. And now I know, oh, yeah, if he got 80% correct out of those 100, that's 80 correct guesses. That's something serious, right? That's something to be believed versus maybe you gave him 5 cars and he guessed one correctly, right? You got a 1 out of 5 chance, 20% chance to guess, so 20%. But if you guess 80%, yeah, your confidence level is a little higher if you can increase that sample size. Right. So here's just the kind of the example that I used, right? So say uh, a researcher wants to test this, right? And so he gives them those 10 trials, and in those 10 trials, these are the probabilities on the right hand in this right hand column here. These are the probabilities of guessing the number of correct answers, right? So it's almost impossible not to guess one right. Right. So there's a 10% probability that you're not going to get any. There's a 27% chance that you'll guess one. There's a 30% chance that you'll guess two correctly, 20% chance that you'll guess three correctly. But as you increase the number of guesses, the probability that you're going to guess that number correctly decreases. Right. So if a researcher set the probability or the significance level at 5%, because 5% is extremely rare, right? 0, 1, 2, 3, and 4 would not be significant because again, anybody can just guess those, and it's not the probability is really is higher than 5%, right? But as you get to 5%, that's 2.6%. That's in that critical region, right? That means it's rare that you can guess 5 correctly, and then anything greater than 5, anything greater than 4, rather, man, it's the probability means that you got ESP, right? Or you're just again a heck of a guesser, right? So that's what we're concerned about. Okay. Just to revisit those 3 basic research questions, when we talk about inferential statistics, you got descriptive. We talked about descriptive and the correlational, the variance, the mean, median, mode, standard deviation, and also looking at those graphs. And then we're looking at relational, right? That's correlation. We're looking at the 2 variables and how they are related to one another, the association between those 2 variables. And then the last thing is causal, and causal has to do with differences. So when we're looking at that example with the model group and the no model group as far as aggressive behavior, we're looking at cause, right? Because we're making the hypothesis that the difference between those 2 groups is because the group with the model, the aggressive model, that's increasing the level of or the number of aggressive behaviors in those kids, and so we're saying that causes that, right? Because again, those students that looked at the aggressive model have higher aggressive numbers versus those who didn't. So that cause, and that's the effect of having an aggressive model. And so now we know, right, when we're talking about hypotheses and inferring to the population, that when you are aggressive around your child, maybe corporal punishment or, just you see abuse in your household, those young people are likely going to have higher incidences of aggression to their peers and those around them. And so we want to mitigate that by creating an environment that is less aggressive and not allowing them to watch various TV shows, play video games at a certain level, because again, we see that aggression that view and are around increases their level of aggression as they move forward in their behaviors and attitudes. Okay. So when we're looking at, again, that causation, right, that third research question, we're looking at group differences. And again, when you're thinking about your research proposals, also think about what test you're going to use. If you're looking at 2 separate independent groups, then you're going to want to use a t-test. If you're looking at more than two groups, then you're going to want to use what we call an f-test or an ANOVA. We're looking at the differences among groups or between two groups, okay? So again, when you use this statistical test, you must first do three things, okay? You must specify your null hypothesis, and the null hypothesis says that there are no differences between the groups at all. Like all the groups are pretty similar. And the only difference that we see among those groups is based on unsystematic random error, okay? When we talk about the research hypothesis, however, that says that it's not just the random and unsystematic error. It also has to do with the effect of whatever the treatment is, right? Whatever we're studying is affecting the independent variable is affecting the differences in the dependent variable. So that's what we're doing. And the last thing is setting or specifying your significance level. And again, that significance level that we talked about, the alpha level, usually 5%. However, some researchers use 1% as that kind of that rarity, or 0.01% if they want to be really, really conservative. But oftentimes we're going to be using that 5% significance level because 5%, you got 95% is, pretty normal, but that 5%, if anything approaches that 5% probability, then I know that it's pretty significant and that there may be a difference. And we see that cause and effect there. Again, here are the t-test. This is how you would calculate the t-test. You see in the numerator, you see your group differences, right? So if we were looking at the group that we talked about, the no model group and the model group, we're looking at aggressive behavior. The 5 point, I forget the number, 5 point something, and then the 3 point something, we subtract those two things. That's the difference between those means. And then we would pull the variance that we looked at in that table at the beginning. We would pull that variance, and then we would be able to get our t-test. So here, again, here's the example down here, right? So it's a 5.20 for the model group. It was a 3.10 for the no model group. The variance for the model group was 1.29. The variance for the no model group was 1.43. You can, again, those two, the N is your sample sizes for those two independent groups, it's 10 each. And then all you do is plug it in, you do the math. And so for our t-test, our t-statistic, our t-value, again, it's the ratio between these two aspects, the group difference and the group variability. We have a t-value of 4.02. And I'll tell you right off, that's going to give me a significant value, right? So when we looked at the t distribution, if you remember the t table, you would go to, in this particular case, the degrees of freedom. We'll talk about degrees of freedom. Degrees of freedom will be 18 in this case because we have a total sample size of 20. 10 minus 1 is 9 for the first group. 10 minus 1 for the second group is 9. And so you add 9 and 9 together. That's your total degrees of freedom. You would go down to 5% significance level. And I don't know what that critical value is, but 4.02 would surpass that. And you would have a significant difference. So that means that with that 4.02 being that high, that means that the aggressive model that the kids in the model group looked at, it affected the number of aggressive behaviors in those students. Okay, so here is the t values, right? Here are the critical values, and so this is how you would draw it out if you remember this from statistics. So for the first one, you have a two-tailed test with a 5% significance level. We're looking at 18 degrees of freedom. And so our critical value, these shaded regions, that is considered my critical region, right? So we do a two-tailed test. We split the 5% into two tails, right? So we have 2.5% on one side, on the right side, 2.5% on the left-hand side. And so those t values is a plus or minus 2.101, right? So when I look at my t score or t value of 4.01 or 4.02, excuse me, that t test is all the way out here, right? So we know that it is extremely rare. And so we know that there's a significant difference there. When you're using a one-tailed test, right? So this is directional. And that means that I would say my hypothesis would state that there is the students who looked at the aggressive model, right, would have a greater mean of aggressive scores than those who didn't, right? And so that's a one-tail test. I'm making a direction, either greater than or less than. For the two-tailed test, I'm using no direction at all. I just want to see if there's a difference at all. Right? If there's no difference, then the t value would fall in this white region, just the same as here. But when that t value falls into the blue region here, that means I have a significant difference. And obviously, with the one-tailed test, with a 1.734, that 4.04, 4.02, that falls way out here again. So you would reject that null hypothesis, meaning there is a significant effect between that model group and the no model. Okay, so we talk about degrees of freedom. The degrees of freedom, those are the number of scores free to vary once the means are known, right? So if I know the mean, let me go back. If I know the mean is 5.20, right? I know the mean is 5.20. I have 10 scores. Okay, I have 10 scores. The numbers and the number of scores in that number of 10 scores that are free to vary is not right because when I input all those 9 scores, I know 10 scores, you take your 5.20, whatever that total is, right? Whatever the total of the number is for the scores, you divide it by 10, I get my 5.20, right? So if I know that 9 of those scores are being free to vary one way or the other, they can be any value, right? But that 10th score has to be a specific value because that 10th score has to give me the average of the 5.20. Every other score can be pretty much whatever, right? But that 10th score has to be something that is going to give me the value of 5.20. When I add it all up and divide by 10, I got to be able to get that 5.2, right? So again, that is degrees of freedom, right? And that helps me to get that critical region that I talked about, the shaded regions. That's what I use for my F test and my T test to be able to get my critical region so that I can compare and be able to make those inferences to the population. Okay, so again, a one-tailed test, the research hypothesis specifies a direction of difference between the groups, so either greater than or less than. With a two-tailed test, the research hypothesis does not specify a predicted direction of difference, right? It just says that there is a difference somewhere, one way or the other, right? I'm not putting a direction either greater than or less than, okay? Again, the second test is, again, the analysis of variance. And this test is when you have, again, more than 2 groups, right? So with two groups, you're going to use a t-test, okay? But when you have more than 2 groups, you're going to use a f-test. And the f-test is going to look at, say you had variations in, say I was looking at the dosages of a particular drug, okay? And I had four separate groups. One group is the control group. They're not receiving the drug at all. The first group is receiving a specific dosage. The second group is maybe receiving a larger dosage. And then the fourth group is receiving the largest of those 3 dosages. And I want to look to see, maybe I'm looking at weight loss, okay? And I try to hold everything constant. I'm looking at weight loss, and I'm looking to see if either of these dosages has a difference and plays a difference in weight loss. And that weight loss is going to be in pounds. That's going to be my dependent variable. And I'm looking at those 4 independent variables, control group, and those 3 separate dosages, right? So I'm looking at the variables, and then looking at how those affect the dependent variable in weight, okay? So again, when a study has only one independent variable with 2 groups, the F and the T are, again, virtually identical. We just got 2 groups. But again, when you increase the number of groups to 3, then you have an issue, right? So you have to use the F test, right? So it's an analysis of variance. Again, it's used when you have, again, more than 2 levels of an independent variable, and when a factorial design with 2 or more independent variables has been used, right? So we talked about that when we talked about designs and research designs, and that's what we're referring to. So with the F ratio, okay, there are two different types of variances that we're referring to. Okay, for the first one, we're looking at systematic variance, and the systematic variance, that is the deviation in the group means, right? That is the mean. There are differences between the means based on the treatment effect, right? That's what I want to see. I want to see systematic differences between each of those four groups, the control group and each of those three dosages. I want to make sure that they are different, right? They are systematically different, right? So again, you have a deviation in the group means from the grand mean, or the mean scores of all the individuals in that group, right? We're looking at those individual differences in those three groups. And then you also have what we call error variance. And the error variance, that's that unsystematic variance, right? That's that random error stuff that the variance is just random. It just happens by happenstance. There are differences between those groups because, again, everybody's individuals, right? So we're all going to be different, and that's going to create some differences as well, right? So the deviation in individual scores in each group from their respective group means, again, those individual differences, that's that, that's that variance. The individual differences, the unsystematic error, that random error, those are the three things that we capture in error variance. Okay. So we want the systematic variance to be higher and greater than the error variance, right? We want to see that systematic variance, the stuff that the independent variable is making the change, making the difference the way it's supposed to be. And then the error variance is that stuff that's random, right? So the larger my F ratio, the more likely it is that the results are going to be significant. That means that the numerator, the systematic variance, should be greater than the error variance. And when I see a big systematic variance and a small error variance, I'm going to have a very, very large F ratio. And when I increase that F ratio, then the likelihood of my results being significant improves and increases. Okay. The second thing that we do, right? So when you determine that you have a significant difference, and even when you don't, you oftentimes want to look at the magnitude of the differences between the groups, right? So if I'm looking at the difference between those two groups, the model group and the no model group, we talk about the aggressive behavior, 5.20, 3.10, that difference we saw was, pretty big, right? That's what 2.10, right, of difference in those means. I want to see what the effect size is. I want to see what the magnitude of that difference is. Is it a large effect size? Is it a small? Is it a moderate effect size? And so with the effect size of R, or R squared, you're going to use this this value here, right? So this is the R squared equation, effect size, and this is looking at the amount of variance that is explained by the differences between those two groups, right? So how much variance is being explained by the group that's looking at that aggressive model, right? If it is really, really high, so say that looking at the aggressive model explains about 45 to 50% of the variance. That is a lot of variance. That means 50% of the variance that we see between those scores is on account of them looking at that aggressive model. And now there may be some other factors that help in explaining the variance among those scores. So they might just be aggressive children. They might have an aggressive sibling, right? But them looking at that model, again, 50% of the variance in their scores is explained by just them looking at the aggressive model outside of just those other factors that might influence it. Okay. The second type of effect size is the Cohen's d. Okay. And the Cohen's d is calculated via this, right? And as you can tell, as you can see here, the Cohen's d does not take into account the sample size, right? So it's only looking at the ratio between the differences in that means and the standard deviations, right? That's all it's looking at, and it wants me to give me a standard estimate of the difference, right? And I want that standard estimate to be greater, right? A higher number for Cohen's d, even a higher number for the R squared at the top here, again, means I have a larger effect size, meaning this greater magnitude of those differences. Okay, so here are some conventions and guidelines for kind of the size of the effect size descriptions. So the strength is listed here: small, moderate, and large. So anything greater than 0.50 is considered really, really large for the R. And then for anything 0.10, that's really, really small, right? For the Cohen's d, anything greater than 0.80, that's a really, really large effect size. That means the magnitude between those means is really, really large. And that means that the aggressive model, those kids looking at the aggressive model, makes a huge impact on those aggressive behaviors in those kids. Okay. One of the last things that we use is a confidence interval, and it's used somewhat as an effect size measure. But what it helps to do is that interval where the given level of confidence, that's where the population values, especially for say the differences that we had, the difference lies somewhere between that interval, and we create that interval using the values that we collect. Okay, and so I'll show you in the next example, but it gives me if I'm 99% confident that the value of the difference between the no model group and the model group is between these certain values, then that's a big range, right? If I am 80% confident, right, then that confidence interval kind of shrinks a little bit because I'm not that confident that the value of that difference is in between those two values, right? So again, your confidence interval plays a big role, and again, it's represented by bar graphs, and we'll see the upper limit and the lower limits listed on the graph, and I'll show you on the next slide. Okay, so if we're looking at the example, we're looking at a confidence interval, right? The model group had a 5.20, the no model group had a 3.10, and when we look at the confidence interval, these are the confidence intervals for this is a 95% confidence interval. That means I'm 95% confident that my population value, so these are sample values, right? But I'm 95% confident that the population for the model group, those who are looking at an aggressive model, is going to fall somewhere between 4.39 and 6.001 for the model group, and 2.24 and 3.96 for the no model group, right? And so I'm 95% confidence, right? So there's 5%. I'm not just not that confident, right? But I'm 95% confident that it's going to fall within these groups, okay? So in this bar graph, you got your bar that is going to be hitting at 5.20. This lower bound right here, that is the 4.39 for the model group, and this is the 6.01 at the top here for the model group there. And then for the no model group, it is again that 3.10. The lower bound is 2.24. It lies within the graph for the bar graph, and then the 3.96 right here at the top there, right? So that's your range, and then you're 95% confident that your true population value for your mean is going to lie somewhere within there. Okay, and that gives me a good indication of how confident. That's the effect size, one of the effect size measures that I use. Okay, so just a kind of an overview, right? Again, the goal when I'm looking at hypothesis testing, I'm looking to see if the results that I've obtained are really reliable, right? And so that's why I do a statistical significance hypothesis test. I want to determine if those results are reliable or not, right? And my significance level that I choose lets me know how confident I am and when I'm making those decisions, right? So I have a 5% confidence interval. I'm at a 5% significance level. That I'm, again, when it reaches when that difference is really rare and it kind of exceeds that 5%, right? So maybe it's 3%, then I'm really, really confident that the results that I obtain are reliable, right? And so when I get a significant results, again, those are more likely to happen when I have a really, really large sample size, okay? So with our two groups, we had an N of 10 for the model group, an N of 10 for the no model group. But in order for us to get something that is, again, really, really, really significant, I could have increased the sample size to 25, to 30, to 40, and that significance level would have shot. I mean, it would have been extremely, extremely significant. no doubt that those differences are really significant. Okay. There are two things that happen. So when we're talking about probabilities, there are errors that can occur, right? So when I make a decision, as far as something being significant or not, there's always going to be some type of error. So when we're talking about probabilities, there's always opportunities for you to get an answer wrong, right? So there are instances where you find a significant value, but it's actually maybe a false positive, right? And sometimes you find something that's not significant, but that's really a false negative. Maybe it's not significant, but it actually really is happening in the population, right? So we have to be really concerned about that. Okay, so the decision to reject the null hypothesis, again, that's saying that there is a significant difference, is based on, again, those probabilities, rather than just basic certainty. We're not certain. We don't prove things. Nothing is 100% accurate. We're just making inferences, right? And so when we decide that we're going to reject the null hypothesis and say that something is statistically significant, all we're saying is that there is enough evidence. There's enough evidence to support that research hypothesis. There's enough evidence to support it. When we fail to reject, or when we kind of go ahead along with the null hypothesis, saying that there's no difference, that means that there wasn't enough evidence to prove or to support that research hypothesis. So we accept the null hypothesis. Okay, and we'll talk about the decision matrix on the next slide. But there are two possible decisions and two possible truths about the population. The first one is you reject the null hypothesis or you accept the null hypothesis. Those are the two decisions, and the two truths are the null hypothesis is actually true when you reject it, or the null hypothesis is actually false when you accept it, right? And so we have to be careful when we do those. And again, the level of our significance, the level of the ability to make these decisions accurately is really based on the research that we design. Our studies that we design help to render us a better opportunity to be more accurate in the decisions that we make. Okay, so here's just a false positive is type 1 error. A false negative is a type 2 error. So a false positive is I'm rejecting the null hypothesis when the null hypothesis is actually true, right? I should be accepting it, or I'm failing to reject the null hypothesis, right? The null hypothesis is false, but it is actually true, right? So I have a false null hypothesis, but it's really true. It's something happened, right? But I accept that false null when it's actually something happening in the data. Okay. So again, the type 1 error here, again, the null hypothesis is true, but you reject the null hypothesis. Okay. With a type 2 error, the null hypothesis is false, but you accept the null hypothesis. So you say that you accept the null hypothesis, you fail to reject it, but the null hypothesis is actually false. And so we run into those areas when we again, the level and the accuracy of the data that we collect is really important, and the design of the study. The type 1 error, that is your alpha level, right? So if my alpha level is 5%, then I have a 5% chance of making a type 1 error, right? That means the null hypothesis is true, but I reject it, right? And so that's a 5% chance of doing that, right? So when I decrease my alpha level, say from 5% to 1%, then there's only a 1% chance that I'm going to reject the null hypothesis when the null hypothesis is true, right? The opposite of that is the beta, okay? And the beta, that is your probability that you're going to make a type 2 error. That means the null hypothesis is actually false, but I accept the null hypothesis anyway, right? And so sometimes that happens just based on a number of factors, and we'll talk about those factors, okay? But again, correct decisions occur in two instances: when you reject the null hypothesis and the hypothesis is true in the population. Again, that's a really good thing. Or when you accept the null hypothesis, that means that there's no difference between those two samples or those two means, and the null hypothesis is true in the population, right? So we want to make those correct decisions, but sometimes with using probabilities, that's not possible. Okay. Type 1 error, again, reject the null hypothesis is a false positive. You reject the null hypothesis, but the null hypothesis is actually true. Again, the alpha level or that significance level is that likelihood, right? So if I have a high alpha level, I'm increasing the likelihood that I'm going to make a type 1 error, okay? The type 2 error occurs, again, when you uh, accept the null hypothesis, when the actual research hypothesis is true. There's a difference, but we don't see the difference in the research, okay? But again, the probability of this type of error, again, is related to three factors: your significance level, your sample size, and your effect size. And we'll talk about effect size here shortly, right? A little bit more in detail, and power, okay? But again, significance level, when you increase in one area, you're again, you're decreasing your probability in another area, right? So if I decrease my probability of making a type 1 error, right, by decreasing the significance level, then I'm increasing my probability of making a type 2 error, right, and vice versa. When I increase my sample size, that is, again, decreasing, right, the likelihood that I'm going to get a type 1 error, right, but it's increasing the likelihood that I'm going to get a type 2 error, right, or vice versa, right? Same thing with effect size. Okay. And again, here's just that when we're looking at an example for a jury trial, right? So in a jury trial, the null hypothesis says that they're innocent, right? The research hypothesis is going to say that no, they're guilty, right? So if in a type 1 error is going to say they are innocent, but we find them guilty, right? We don't want that, right? We don't want to send innocent people to jail. So that's a type 1 error, that's a false positive. Okay. The other side is the person is guilty, but we find them innocent, right? So they did it, like OJ, they did it, but we acquitted them, right? The glove didn't fit, so we had to acquit, right? And so that happens as well. And so we have to be mindful of that as we start making decisions. And that's kind of a false negative. Okay. All right. Okay, so choosing a significance level, we're not going to belabor this point. But again, researchers have traditionally used 5%, 0.05, and 0.01. And again, this significance level is, again, the decision to reject the null hypothesis. So choosing the level specifies the type of, again, the probability of a type 1 error if the null hypothesis is rejected. Again, the level chosen and the consequences of a type 1 false positive or a type 2 false negative error are determined by the use of the results, right? So again, if I'm increasing the probability, or excuse me, decreasing the probability of getting a type 1 error, I'm going to be increasing the probability of getting a type 2 error, and vice versa. Okay. And so another example. So you decide to get COVID tested, right, based on your mild symptoms. And there are two errors that could potentially occur, right? Type 1 error, you do a false positive. That means the test results say you have coronavirus, but you actually don't, right? We had that where a lot of people were getting false positives, right? Or you get a type 2 error, you have a false negative, right? The test results say you don't have coronavirus, but you actually do. And that happens sometimes too. But again, I would much rather, get something that is, the type 2. That's kind of bad, right? Both of them are bad, right? Because I don't want either to happen. But which one would you prefer, right? Just ask yourself that question, right? Ask yourself that question. For instance, and it depends on the context, right? In the jury trial, I don't want to send an innocent person to jail, and I don't want to release somebody who actually committed the crime. But again, I would prefer, to get a false positive. I'll be safe anyway. I don't have it, than not get a test, say I have COVID, and then I'm out here spreading COVID to everybody else, right? Again, so that's depending on the context, what really matters. Okay, but for the when we talk about rejecting the null hypothesis, when the null hypothesis is actually true, that's, in research, that's not always a good thing, right? That's not always a good thing because now we're giving false results, right? So if somebody would try to replicate it, and they'd be like, man, well, he got a significant result, but again, it was actually false anyway, right? So it was really no difference at all but we saw a significant difference in our results. So again, in research, type 1 error is not all that great. Okay. So interpreting non-significant results. So sometimes that happens where we don't see a significant result. We don't see a significant difference between those two scores. But what happens is you can use an effect size measure to see if there's a magnitude, right? So even and again, contextually, that makes a big difference because in the medical field, if I want to use a particular medication and I want to decrease the size of a tumor, right? A half of a centimeter, a millimeter makes a big difference, right? So maybe it's not significant, right? But maybe it's really meaningful, right? With the effect size, maybe it's extremely meaningful, and again, that makes a big difference, right? So again, a meaningful result can be overlooked when the significance level is very, very low, right? But again, increasing the sample sizes, again, you can, when you increase your sample size, you're going to increase and again increase that the effect, which then gives you a larger effect size. Okay. The second thing that we do before a study, right? So we want to know what our effect size is, right? So we try to predict it, right? We do our alpha level. We also try to predict what effect size we want to see in our results, and our power analysis lets us know what sample size I need in order to get the effect size that I want, right? So when I want to increase power, I have to increase the sample size. So sometimes increasing the power gives me a bigger sample size, right? Or yeah, increasing power, I need a bigger sample size. So smaller effect sizes are going to require larger samples, right? To be significant at a 5% significance level. And a higher desired power demands a greater sample size, okay? And researchers typically on a convention usually want a power between 0.7 and 0.9 to determine what their sample size is going to be, right? Because again, being realistic, your sample sizes have to be, they have to be small enough that's manageable, but they can't be really, really large where it's not feasible for you as a researcher, right? But again, I want to determine what my sample size is going to be or needs to be for me to get a specific difference in effect size for my research. And here are the conventions. You have a 0.8, 0.9 power, right? And as you see, right, when you look at the effect sizes, when you're looking at a large effect size, with these power, you don't need a really, really large sample size. So 36 for 0.9, 26 for 0.8. But as you see, if you have a really, really small effect size, right, you need a really, really large sample size, right? 1,052 for 0.9 power, 789 for 0.8 power. So again, the higher your power, the more, the larger your sample has to be for you to detect a small effect size. Okay. One of the other things that we talk about is replication, right? And that's why I talked about with the proposals. When you're doing your method section, the recipe, right, your procedures and your participants and your methods, your participants, your materials, and your procedures play a big role. I need to know specifically what you're doing so that I have a better chance of replicating it after you get your results, right? Because if you have some groundbreaking, earth-shattering research, right, to say that it's significant is not enough for one researcher, right? But if I have 100 researchers doing the same study, getting the same results, then I know that I have something that's really, really impactful, and I know that the research can be replicated and then generalized to the population, right? So again, a rich understanding of the phenomenon comes from, again, results of numerous studies investigating the same variables over and over and over again, right? So the aggressive model experiment or research, again, if I'm doing that study in the United States, I'm doing it in Europe, in Africa, I'm getting those same results, then I know that the phenomenon is pretty accurate. It's pretty true. Okay, but again, you want to look at those results of the studies, and you'll want to be able to replicate those investigations, those previous investigations. That's the whole key for me talking about being really, really specific with your research proposals. Okay. One of the only other things that we talk about is the correlation coefficient, we're looking at the significance of the correlation coefficient. The higher the correlation, the bigger the likelihood that you're going to get something significant, right? But you want to make it a decision, right? So if it's a really, really high correlation, but you don't have as much of a big sample, then that plays a big role, okay? So again, Pearson correlation, it describes the strength of a relationship between two variables. And again, when you have both of those variables either going and increasing in the same direction or increasing in the opposite direction, you got negative correlation. In the same direction, either up or down, you have a positive correlation, all right? But again, you want to see if that correlation is statistically significant, right? So you decide whether to reject the null hypothesis, meaning that when you reject the null hypothesis, there is a relationship. When you fail to reject it, there is no relationship whatsoever, right? So you want to conclude that the true population correlation is in fact greater than 0, right? Meaning it's a significant population correlation, okay? Here are some examples of some major statistical programs that that I've used. Specifically, I've used SPSS. I've also used R, which is a kind of a freely open source statistical software tool. But we use those, and I've also used Microsoft Excel. That's how I learned how to do t-tests and correlations and ANOVAs right off, right, doing them by hand. But again, when you can do a simple analysis, you can just use those spreadsheets in Microsoft Excel, and I've done that before as well. But you use these instead of having to do a t-test or an ANOVA correlation factor analysis. You can use some of these software, some of these statistical programs to run it. You click a button. First off, you put your data in. You set the parameters. You press your button for what type of test you want to run, the assumptions that need to be met, and boom, it spits out an output, and it gives you everything that you need. Okay. But again, once you get those results, it spits you out an output, right? And you have to be able to interpret the output. And there's an example next that shows you kind of an output that you would see from SPSS. But again, it gives you your data. You click and determine what test you want to run, and then it gives you the results of your study. Okay, so here you see an aggressive score, right? So you have a model group and a no model group here, right? So I think 1 is for the model group, 2s are for the no model group, and then they put it together, right? So you got a model group, you got a no model group. You see here, the model group, you have a 5.20. We're just using the data that we used at the beginning. 3.1 for the means. You see the variances. You see the number of observations or the number of participants in each of those groups. You see the pooled variance there, the degrees of freedom, like we talked about. Those are the number of scores that are free to vary. You see the T statistic here, right? We got that, 4.025. Here is my critical value for the one-tailed test. Here's my critical value for the two-tailed test. And as you can see, this T value, the probability that is a one-tailed test is very, very low, right? That's very, very rare. That means you would reject the null hypothesis. You would also reject the null hypothesis here, right? Because it's a 1, yeah, and so 1, 2, it's a 0.1% probability, right? That means again, you got a 5% significance level, it's 0.01%. That means you want to reject the null hypothesis. There's a significant difference between the model group here and the no model group there. Okay. We'll talk about the ways in which we talk about those different significance tests. But again, it's really based on the data that you're collecting, right? So we have nominal, ordinal, interval, and ratio scale properties, right? Each of our different significance tests that we use is based on the data that we collect, okay? And if you need any help with your research proposal determining what statistical test that you'll need, again, I'm more than willing to help. But again, the type of data that you're collecting plays a big role in what type of test you'll be doing for your statistical test, okay? So we'll talk about those things, continuous variables, discrete variables. All of those things play a big role in what you're going to do with your variables, and then what you're going to, how you're going to statistically analyze those things. Okay, so if you're looking at nominal variables, right, you got your IV, your DV are both nominal, right, chi-square. Okay, if you have two nominal variables and then you have your DV is an interval or ratio, it's a t-test. If you have more than two groups that are nominal or IV, then your DV is interval or ratio. You have a one-way analysis of variance. If your IV and your DV are both interval and ratio, then you're going to have a Pearson correlation. It means they are both numerical values. Your optimism score and the number of sick days last year, that's going to be a Pearson correlation. Okay. And then the last two, you have, again, two or more variables that are nominal, and your DV is interval versus ratio. Then you have analysis of variance. You can have a factorial design. And then the last one is when you have two or more variables that are interval or ratio, and then you have an interval ratio DV, that means you're going to have a multiple regression. You're making a prediction. So you have two variables that maybe vary at a particular level, and it affects the level of your DV. That's going to be your multiple regression. So again, you're going to use these tables to kind of get an idea of what your variables are. So if we go back to the two groups, right? We're looking at the ACT, right? We got a pre-test, we got a post-test. I know that I'm going to be using a t-test because I have a pre, I have a post. Those are going to be two. Let me go back here. So those are, again, two different groups, right? Two different groups of scores, a pre and a post, right? But I'm using a interval ratio scale. That's the ACT scores. And so that'll be a repeated measures t-test because I got a pre and a post. If I were looking at two separate groups, maybe I was looking at a group of high-income students, a group of low-income students, and I was looking at ACT scores in those two particular groups. That'll be, again, two groups. That's nominal, low income, high income, looking at ACT scores. That would also be an independent measures t-test. Again, just looking at those different types of research studies. Okay. But again, that is all I have for today. It was a long lecture today, maybe about a minute and 10, but covered a lot. Make sure you're using your time wisely to complete your research proposal. If you need any help, I have office hours again throughout the week, 9 to 1 on Tuesdays and Thursdays. Tuesday is in person. Thursday is virtual usually. And then on Wednesday, I have 12 to 2 office hours. So if you need any help, please reach out and set an appointment. Set some time aside to come to ask for help. Right here are the review and discussion questions. Use these for the exam that we'll have on the 27th, I believe, of April. That'll cover the last 4 chapters. So be mindful of that as we move forward. Okay, if you can answer these questions, you'll be pretty good come exam time. Okay, but I hope you all are having a great evening, and I will see you all next week. Again, I'm gonna record the final lecture, which will be chapter 13, and then that'll be the last chapter that is covered on the exam. Okay, I hope you all are well, and I'll see you all soon. Take care.